Assalamualaikum and hello. My name is Muhammad Hakimi bin Muhammad Tajuddin, matrix number 228498, and we will present on our strength of materials 2 assignment, which is titled Upright Table. Okay, so to give a brief introduction and description of the structure we chose. So first of all, we collectively agreed to choose an upright table in our classroom as it aligns with the syllabus of the course that we enrolled. It involves a rectangular beam that is subjected to axial loads. So, but in this case, it's not fully a bar of rectangular beam. It is instead a hollow steel tube that's still a rectangular shape. So that's about it for the description of the structure itself. So according to the photos that we have taken, it can be shown that the load is being applied from the tabletop to the apron of the table to the legs, which is 4 in quantity, to the floor. So this could mean that the legs, or each and every single leg, is taking the load of the tabletop and the apron of the table. And in realistic what do you call scenarios, it would be pencil cases, tablets, laptops. One third of a human being's body weight would take into account of the table itself. And based on our observation and based on these photos, so far the table has not undergo buckling, which means that it has not failed at all. So it's functioning properly and it's still good in use.
Hello, my name is Mika Nik Faisal, matrix number 230833, and I will be explaining about the engineering explanation of behavior. So for our topic is buckling. When a vertical compressive load is applied to the table surface, the force travels axially down the natural axis of the hollow steel legs. Below a critical threshold, the legs compress elastically, preserving their straight alignment and transferring the force directly to the supporting table below. However, since these legs act as a slender column, their structural behavior is determined by geometric stability rather than the yielding strength of the steel itself. So once the load exceeds the critical limit, the legs buckle. The system shifts from a stable axial compression to structural instability. This is demonstrated when the leg bows outwards perpendicular to its longitudinal axis, signifying a sudden and lateral deflection. This transition instantly shifts the internal stress state from pure compression to a combination of bending and compression. The direction of this lateral displacement is entirely predictable, where the leg will always bow along its weak axis, which corresponds to its minimum radius gyration and lowest bending resistance. Now we're moving forward to the sketches and diagram. So on the left, we can see that there is a diagram of the geometric profile. So the dimensions are stated as the height is 600 millimeters, the length is 30 millimeters, and the width is 30 millimeters. So for the thickness of this slender hollow leg, it actually has a thickness of 2 millimeters. Now moving forward to the next diagram, we have a diagram that shows the buckling of the leg. So over here you can see when the load is applied at the top of the leg, there is a buckling, which is a bowing to its weakest axial component. So over here you can see that its original state, which is straight, becomes a bowing-like structure.
Hello, my name is Vimal Parandaman, matrix number 229843, and I will be explaining on the engineering implications of our report, which is based on buckling of a folding table. First, we will talk about the symmetrical stability. The 30 by 30 millimeter hollow square section design offers a uniform resistance to lateral deflection in all directions due to its balanced geometric profile. But the extremely thin 1 millimeter walls introduce a severe structural risk, making the legs highly susceptible to localized plate crippling before global bowing can occur. If the local buckling is triggered, the square cross-section instantly crushes, resulting in total and immediate structural collapse without any visual warning. The unbraced free pin connection at the floor effectively increases the column length, which drastically reduces the maximum critical compressive load the leg can withstand. For the required safety margin, a rigorous factor of safety must be applied to the maximum allowable weight rating to ensure everyday loads remain strictly within the bounds of pure elastic compression. Now, moving on to the conclusion. The primary limiting factor is that the table's load-bearing capacity is governed mainly by geometric instability, rather than the ultimate yield strength of steel. Dual failure modes are that the slender legs, 600 mm in height and 1 mm in thickness, are highly susceptible to both global lateral bowing and local plate crippling. For the sudden risk of collapse, the extremely thin 1 mm walls pose a critical risk of localized buckling, which can trigger immediate structural failure without any visual warning. The reduced capacity is that the table's boundary condition, acting as a free or pin connection at the floor, significantly lower its theoretical maximum load capacity. And lastly, for the safety requirement, a robust factor of safety must be applied to the maximum allowable working load to ensure the legs remain safely in a state of pure elastic compression during everyday use. Hello, today we are going to do a strength of material assignment on buckling analysis. And for the structure that we have chosen, it is this folding table that we use in our everyday class. This buckling analysis starts with placing a load on this table.
So over here we have our everyday item as acting as our load. So from this load we can tell that each of the legs, 4 legs, undergo axial compression where buckling may occur. So let's get into the dimensions of the leg. So for this leg, it's a hollow 3 by 3 centimeter leg with a 60 centimeter length.
Why do we have to do buckling analysis? It is to make sure that this structure can withstand the load that it is made for. For example, it has to be able to withstand a human being writing on it while applying force using their hands.
Thank you.
Thank you.
And that is all from us.